Hi folks, in this video we're going to start by taking a look at some examples of simplifying expressions that have different kinds of exponents, and in particular I want to look at some conventions that we tend to follow when we're simplifying these expressions with exponents. Okay, so a couple of things I want us to recall, okay, from most likely from last year, and it has to do when we're taking powers of products and quotients. Okay, so as an example here, if I have a product of two expressions and I take that to an exponent n, we can distribute this exponent to each of the expressions in the bracket. So this is equivalent to a to the n, b to the n. Okay, and similarly we can do the same when we're working with quotients. So if I have the quotient a over b to the exponent n, I can distribute this exponent to each part of the quotient. So this is a to the n over b to the n. Okay, and we're going to keep this in mind as we're doing some of these examples. Okay, so let's take a look at some of the conventions that we follow when we're simplifying these expressions. And the first we'll look at has to do with negative exponents. Okay, so let's say I take this example here. Okay, so I have 3x to the negative 2, y to the 5. Okay, the first convention we follow is that we tend not to use negative exponents in our final answer. Okay, we'd like our final answer to have all positive exponents. So how can we take this expression here and write as an expression that has only positive exponents? Well, this is just a coefficient, so that won't change. Here, y to the 5 is not a problem. It's this x to the negative 2. Okay? And this is where we remember that x to the negative 2 is just equivalent to 1 over x squared. So if I do this the long way, normally I wouldn't show all these steps. But what's going on here is you've got 3 times x to the minus 2 is the same as 1 over x squared, and then times y to the 5th. Okay? And when I multiply these terms together, I just end up with 3 times 1 times y to the 5th. So the numerator is 3y to the 5th. And in the denominator, well, this is like 3 over 1, y to the 5th over 1. So I multiply all the denominators, and I'm just left with x squared. Okay? So normally, I wouldn't bother doing this step here. I would just see that I've got an x to the negative 2, so I know that that's going to be going into the denominator. Okay? What if, though, our negative exponent it's itself in the denominator? Okay, so let's say I've got 3y to the 5th all over x to the negative 2. Okay? Well, again, if we write this as 3 times y to the 5th times 1 over x to the negative 2. Okay, let's just take a look at what this expression means. Okay, this expression here, if I look at it separately, well, it's 1 over, and what is x to the negative 2? It's just 1 over x squared. Okay, and this is where we remember one of our basic arithmetic operations, division of fractions. Remember that dividing a fraction is done by multiplying the reciprocal. So if I'm dividing 1 by 1 over x squared, that's equivalent to multiplying 1 by x squared over 1. So that's just x squared. Okay? So in the end, what will this be equal to? This x to the negative 2 in the denominator is just equivalent to x to the power 2 in the numerator. So this just would be 3x squared y to the 5. Okay. Now normally we don't go through the whole process of showing why this occurs. We just sort of remember, well, here if I have a negative exponent and the power is in the numerator, well, I just bring it down to the denominator. And if I have a negative exponent in the denominator, well, that just gets brought up into the numerator. So normally we'll just remember the pattern, and we don't have to show why this is occurring every time. Okay? So another convention that we tend to follow has to do with the last thing we saw in the other video, okay, which is when we have fractional exponents, we don't leave them in fraction form. We'll always write them in root form. So if I have, as an example here, if I have 5 x squared y cubed to the 3/5, okay, we would never leave the expression like this. Okay, convention says that we'll always write this in root form. Okay, so here it makes more sense to first consider the cube, because that'll allow me to simplify this expression here. So this can be written as the 5th root, okay, of 5x squared y cubed cubed. Remember, there were 2 ways to consider this expression: is to first take the 5th root and then cube it, or to first cube it and then take the 5th root. Okay, and we saw that when we were evaluating, when we actually were working with a specific number, we tended to take the root first. But here, I'm not going to be actually evaluating this expression. I'm just going to be simplified. So it makes more sense to take the cube, because now I can actually simplify what's inside the square root. Okay, again, remember our properties here. I can distribute a power to a product. So this just becomes 5 cubed. So 5 times 5 times 5 is 125. Okay, x squared to the power 3. So I can just multiply the exponents. X to the 6th, and then y cubed to the power 3 is just y to the 9th. Okay, these two things are completely equivalent. However, convention says that we don't leave fractional exponents in our final answer. Okay, so as a note here, so you should add this to your notes on exponents. Okay, by convention, when simplifying expressions with exponents, okay, we always avoid giving a final answer with a negative exponent or a fractional exponent. Okay, we avoid a final answer with negative exponents and fractional exponents. Okay, so what we're going to do now is we're going to take a look at a few examples of simplifying expressions with exponents. Okay, so let's take a look at this first example. So again, we've got an expression that's got a whole bunch of exponents, and we want to try to write it in simplest form and using the conventions that we talked about. Okay, so when you've got an expression like this, you want to simplify the types of expressions that you can actually simplify. So here we notice that we've got our coefficients, just our numbers in front, so we can simplify these. So let's start with that. As you've got 20 and 4 can be simplified as 5 over 1. Next, we've got, okay, so we'll keep that there. We have x to the 4, and in the denominator we have x to the 1. So we know that this can be simplified using the second exponent law, the division law. So here we've got x to the 4 over x to the 1. 4 minus 1 is x cubed. Okay, now since the exponent is positive, I'm going to leave it in the numerator. Okay, but now let's take a look at y to the negative 5. I notice that there's no other expressions in y, so I can't simplify the exponent. However, I don't like having that negative exponent. So here y to the negative 5, this can be brought into the denominator to give us y to the 5, positive 5 in the denominator. Similarly, I've got z to the negative 2 in the denominator, no other z's that I can simplify with it, but I don't want to leave this negative exponent. So when the negative exponent is in the denominator, I can deal with that by just bringing it into the numerator as z squared. And this would be the simplest form for this expression. Okay, so simplify the coefficients, simplify any common powers, meaning powers that have the same base, and then just make sure that any negative exponents are rewritten as positive exponents. Okay, let's go on to another example. Okay, let's take a look at this example 2 here. So we've got the cube root of this big expression. Problem here is that it's difficult to actually use the exponent laws when it's in root form. So the first thing that you would want to do in this scenario is to change this cube root into an exponent, because then that'll allow us to use our exponent laws. So the first thing I'm going to do is I'm going to rewrite this as 64 x to the 12 y to the 5. Now, while I'm at it, I notice this z to the negative 3. I'm not too happy about that z to the negative 3 because I know I don't want in my final answer a negative exponent. So right off the bat, I'm going to put that z to the negative 3, z to the 3, of course, when we bring to the denominator, right off the bat. And then all that is to the exponent, 1/3. But now I can use the property of distributing by exponent to each of the terms, because all I have is products and quotients. Okay, so let's do that here. So I've got 64 to the 1/3, x to the 12, all to the 1/3, y to the 5th, to the 1/3, and then in the denominator z cubed to the 1/3. Okay, so now I can start simplifying this. Now here, this is actually easier now to put this back into root form, okay, because now I can actually take the cube root of 64. In fact, it's a very nice cube root. Okay, this here though, I'm going to leave this in exponent form so that I can use my exponent rules. Okay, because I have a power of a power, so 12 times 1/3 is just 4. So this just simplifies to x to the 4. Here, there's no simplification, so this remains y to the 5/3. Okay, and now in the denominator, well, again, I can use my exponent rule. 3 times 1/3 is equal to 1, so that simplifies quite nicely. Okay, so now here I can actually take the cube root of 64. Okay, so do it in your head. So 4 times 4 is 16. 16 times 4 is 64. So that means the cube root of 64 is just equal to 4. X to the 4 here. Nothing left to be done here. Y to the 5/3. Remember our convention. We don't want to leave this as a fractional exponent. So I'm going to separate out the 5 and the 1/3. Okay, and remember we said when we're not actually evaluating the expression, what we tend to do is first take the positive integer power, so y to the 5th, and then the cube root of that. And then in the denominator, we've got our z. Okay, so this would be the simplified form of this original expression. Okay, following all the conventions that we have. Okay, let's take a look at one more example. Okay, so this last example here has got a bit of everything in it. And there's more than one way in which you can start the problem. Okay, I might right away look at this negative and the exponent and right away take the reciprocal of that base. Okay, I might want to take that negative 2 as a whole exponent and distribute it to each part. Okay, since it's all products and quotients. Okay, what I'm going to do though is I'm actually going to just try to simplify the base, meaning this whole expression in the brackets, and then I'll deal with the exponent negative 2 at the very end. Okay, I suspect that's going to be the way that'll probably be a little simpler. Okay, so let's start here. So again, let's start with the coefficients. We've got 12 over 8. Well, that simplifies. Well, they're both divisible by 4. So that leaves me with a 3 in the numerator and a 2 in the denominator. Okay, let's see what we have here. We have x to the 4 divided by x to the 12. So 4 minus 12 is negative 8. Okay, so I don't want x to the negative 8 in the numerator. Right away, I'm going to put that in the denominator as x to the positive 8. Deal with the y's. Y to the 6 divided by y to the negative 1. So I'm going to subtract 6 minus negative 1 is 6 plus 1 is 7. So the exponent is positive, so it'll stay in the numerator. Okay, now we've got z to the negative 5 over z to the negative 5. Well, negative 5 minus negative 5, that's negative 5 plus 5 is 0. So I've got z to the 0, but that's just equal to 1. So there's no point in writing it down. I mean, if I really wanted to, I could write that 1 there. Another way of thinking of this is by itself is just equal to 1. Okay? So we've already simplified that quite a bit. Okay? What I'm going to do next is I'm going to say again, what does the negative in the exponent do to the base? It gives me the reciprocal. Okay? So next thing I'm going to do is I'm just going to take into consideration the negative portion of that exponent, which is just going to give me the reciprocal of the base. So here I have 2x to the 8 over 3y to the 7. Okay, now since I've taken into account this negative already by taking the reciprocal, it now becomes positive. And now in my final step, I'm going to distribute this exponent to each term in the base. Okay, so this is 2 squared is 4. X to the 8 squared, I multiply the exponent, x to the 16. And then in the denominator, I've got 3 squared, so that's 9, and y to the 7 squared, so 7 times 2 is 14. And this is the simplest form of the final answer. Okay. Now you might try to do this problem starting a different way with the same final answer. Okay, so best way to deal with these types of expressions is to practice simplifying them. Okay, that's it for now.